I'm starting.
Okay, Dinesh, start.
Yes, sir, I'm starting.
All right, and shall we start? Huh? Hello? Dinesh.
Yes, sir.
Okay. Still they are coming, huh?
No, sir.
Shall we start now? Shall I introduce? Hello.
Yes, sir.
Okay, now we will start, huh? Shall I introduce?
Yes, sir.
So on behalf of everyone here, I welcome Sivaraj sir as a
Thank.
examiner. Nice to have you
Yes.
here, sir. Hope you have enjoyed this event. Okay. Yeah.
Okay. I thank you. I welcome you all for the PHD Viva-Voce examination of my student, M.Dinesh Kumar, and his thesis title is Lie group transformations on the conducting flows with suspended hybrid nanoparticles. And the total duration is 30 minutes, Dinesh, and 15 minutes for the question and answer. So you have to finish in 30 minutes. So just try to finish, and we'll have a question answer session. Thank you, sir. I'm handing the session to Dinesh. You can start your session.
Yes, sir. Yeah, good morning to everyone. So welcome you all for today's PhD final Viva-Voce. My name is Dinesh Kumar under the guidance of CSK Raju. Now I am going to present my thesis entitled Lie group transformations on conducting flows with suspended hybrid nanoparticles. Next. And this is the overview content of my presentation. The chapter 1 contains introduction. In the introduction part, what are the I used in my study like Lie group transformations, magnetic hydrodynamics, and hybrid nanoparticles, etc., and machine learning, so multilinear regression response surface, those techniques that definitions I kept in introduction. And second chapter contains literature review, and in literature review, and when I study the research articles, and from their findings, I observed that they did with the Lie group transformations with the base fluids only. So in my study, I did Lie group transformation with hybrid nanofluids with various effects that I analyzed the heat transfer rate. And chapter 3 to chapter 9 contains what are the work I did in the form of any research articles. And chapter 10 contains the conclusion. In chapter 3, I considered ternary hybrid nanofluid that 3 nanoparticles are with uniform shape and mixed with the base fluid, and the effects I consider is heat source and sink and magnetic effect. And statistical analysis multilinear regression technique has been applied. And in chapter 4, in ternary hybrid nanofluids, particles with the different shapes like spherical, cylindrical, platelet with different shapes I consider. Effects applied are heat source and sink and magnetic effect. And in chapter 4 also multilinear regression technique has been applied. When it comes to chapter 5, that nanoparticles has been considered with different shapes like spherical, cylindrical, platelet, and response surface technique has been applied, and the sensitivity analysis technique has been applied in chapter 5. So when it comes to the chapter 6 and chapter 3, 4, 5, I applied shooting method like input BUP 4C solver and BUP 5C solver. When it comes to the chapter 6 and 7, I used the spectral method. And that in chapter 6, I applied the in chapter 6, non-uniform shapes only, like spherical nanoparticles are with non-uniform, like spherical, cylindrical, platelet, those shapes are. Response surface technique has been applied, and the effects are means porous medium effect, and radiation has been applied, viscous dissipation has been applied. And next, when it comes to the chapter 7, the variance from chapter 6 and 7 is that whatever I applied in effects in chapter 6, that same effects I applied in chapter 7. Also further suction effect I applied, and the nanoparticle shapes are uniform, and multilinear regression technique has been applied. So when it comes to the chapter 8 and 9, the new thing that I did, I applied the machine learning technique to gradient descent method that I validated with the numerical result. And MLR technique has been applied in chapter 8, and the effects I applied is non-linear thermal radiation and buoyancy force I applied. So yeah, that are the new things I applied in chapter 8. So when it comes to the chapter 9, from the chapter 8, what are the effects I applied? The same effects I applied in chapter 9 also. Further, I applied suction effect and partial slip condition has been considered in chapter 9. So final chapter 10 contains the conclusion. This is the chapter 1 introduction, and fluid mechanics is again having the two parts, a fluid static and a fluid dynamics. So the analyzing the fluid at rest, it is belongs to the fluid static, and when the analyzing when the fluid at motion, it is belongs to the fluid dynamics. So again, that fluids are two types, compressible and incompressible, and if the fluid's density is varies means that is compressible. Example, you can say air, and incompressible means that if the fluid density doesn't vary, you can say example water. Next, Newtonian and non-Newtonian. So that the fluids which will satisfy Newton's law of viscosity, that is known as Newtonian fluids. It doesn't satisfy, that are known as the non-Newtonian fluids. Example, you can say that water. Water belongs to the Newtonian, and for non-Newtonian, you can say some paste, toothpaste, okay, which is having high viscosity. Next, Lie group transformation. In my study, I used the Lie group transformation that to convert that given, that means governing equation to convert that PDE to ODE. And these are the governing equation that continuity equation that mass is conserved, momentum equation. That momentum equation is can be derived by using the F equal to ma, Newton's second law. And third one is the energy equation. So from that we can come to know that energy is conserved, and that when it comes to the boundary condition and initial boundary conditions, from that we came to know that initial state of the system and boundary conditions again three types are there. If there is no gradient in the boundary condition, means it is known as Dirichlet boundary condition. If there is a gradient changes in the boundary, that is known as a Newman boundary. And if that both mixed are there, suppose one derivative term is there, one gradient change term is there, and one normal term is there, that type of boundary conditions are known as Robin boundary value. Hybrid nanoparticle. So it has been invented by Choi, and those size is 1 to 100 nm. And if you mix that two or more hybrid nanoparticle properties into a base fluid, it is known as the hybrid nanofluid. And this is the preparation procedure. And next slide, this is the stretching surface. This is how that for some of the industrial purposes it can be useful, and these are some of the applications of nanofluid, cooling of microchips, and industrial cooling applications, cancer therapy, and for batteries preparation, oil preparation, and to prepare the biological instruments. Right. Magnetic effect, whenever we will apply the magnetic effect, the conducting nature, electric conductive nature will increase. So due to that reason, temperature profile will increase, and whenever we will apply this one, magnetic effect, that to the flow opposite direction, Lorentz force will apply, so it will resist the flow. Here that in this slide contains response surface optimization and multilinear regression. So what is the main purpose of using response surface optimization is, with the less data we can get the optimization condition. So what is the use of applying multilinear regression means that how the independent parameters are affecting the dependent parameter we can analyze. And this is the flow chart, how it will work, like multilinear regression and response surface. Okay, what are the parameters it was affecting, that we will choose, suppose Nusselt number. For Nusselt number we are doing the multilinear regression, means what are the parameters are affecting Nusselt number, that parameters we will consider and we will do. This is the machine learning technique. What is the main use of machine learning technique? With the present data, you can predict the future outcomes. And this is the, in my study, I use a gradient descent. That there you can see that that's how that a gradient descent will work. So simple linear regression means y equal to mx plus c. Its journey will start with m equal to 0, c equal to 0, slope and intercept both will be 0, and it will based on the epochs, we need to give epochs, and learning rate also we only need to give. So based on that, it will continuously number of times it will repeat. Whenever that, here you can see that MSC and mean square error and residual mean square error, that when it becomes almost 0, then it will stop. So this is how that it will work, machine learning technique. And this is the two numerical techniques I have been used in my study. So one is shooting method, BEP force and BEP 5C by using both, and another one is spectral, and the spectral method is the non-linear equations, whatever they using that are almost highly non-linear and coupling nature. In the spectral method, the procedure is non-linear equation is going to be converted into a linear. So that based on the governing equation, we will choose the residues. That how we will choose that and all in one chapter I kept in a detailed way. So later, by finding that Ax equal to R, we will write in the form of Ax equal to R. So then results will be in the form of graphs and data. That is about the spectral method. And when it comes to the B4C package, higher order equations by taking suitable assumptions, we will convert into a first order. And this boundary value problem is going to convert into an initial value problem. Then it is going to be solved. That you will get the result in the form of graphs and tables. It is the literature review. So already I said that previous research they did with the Lie group transform with base fluid only. So in my present study, I am going to analyze the hybrid nanoparticles mixing with the base fluid and analyzing the heat transfer rate. This is chapter 3, and here you can observe whenever magnetic I applied that here in red mark, you can see that Lorentz force is applying opposite to flow direction, and the dual slip conditions will be applied at the wall, and nanoparticles has been considered that are the graphene carbon nanotube, aluminum oxide in case 1. In case 2, zirconium oxide, magnesium oxide, copper oxide with the base fluid as a water. And 3.1 will represent the continuity equation, and 3.2 will represent the momentum equation, that you can analyze the momentum of the fluid, and 3.3 will represent the energy equation, so you can find the temperature. And here that sigma b square, that term will represent the magnetic, and here q naught t minus t infinity, that term will represent the heat source or sink. In this study, I am going to apply the heat source. And further, these are the boundary conditions. Here D1 will represent the thermal slip factor, and L will represent the velocity. L will represent the velocity slip factor, and 3.4 and 3.5 are the boundary conditions. So at present in the form of dimensional quantities. Now further in further steps, I am going to convert by using suitable transformations. I am going to convert dimension to dimensionless. Yeah, so now we can see that by using the above transformation 3.6 and 3. We will get the dimensionless equations 3.7, 3.8, 3.9, and these are the transformed boundary conditions 3.10, 3.11, and these are the stream function. Yeah, this one here. Next, whenever we will, from the Downing equation, whenever we will substitute the stream function, we will get that 3.1 to 3.13, and obviously continuity equation will satisfy. Like these are the transformed boundary conditions. By putting, whenever we will put that stream function in the Downing equation, these are the resulting equations. Resultant Downing equations and boundary conditions. Yeah. This is the Lie group analysis. Okay, these are all the terms are like that similarity transformations using for the Lie group, and the exponential function has been used, and there should not be any variation. That means whatever the factors are here, that whatever the coefficients are there, that all must be equal. So it will tell that there is no any loss. Okay, that's why we are equating all coefficients here. Okay. And we are equating all the coefficients. Further, whenever we will solve that, we will get record results. That is solving by using variable subproblem method. Okay. Yeah, here you will get, okay, similarity transformations you will get. This you will substitute. After substituting stream function, you got one Downing equation. Nah? From that equations, if you substitute this means this 3.29 means you will get below equation 3.30, 3.31. And these are the dimensional parameters, the magnetic parameter, heat source, and Prandtl number. Yeah, these are the boundary conditions. And here B will represent the thermal slip, and their alpha will represent the velocity slip. Yeah, their CF will represent the skin friction, and NU will represent the Nusselt number. These are the viscosity model. So for the ternary hybrid nanofluid, 3.36 will represent the viscosity model, and it is for the density 3.37, and 3.38 will represent the for specific heat. It is 3.39 will represent for ternary hybrid nanofluid thermal conductivity model. And by taking the suitable assumption that for this the thermal conductivity specific heat, we will choose some assumptions. That means entirely you can't put that big equation should be like in the Downing equation. We will choose some A1, B1 like that. So again, we will put that into a Downing equation. That resultant equations are 3.40, 3.41. Yeah, these are the assumptions I taken. This is the numerical procedure that I am using in this unit. That are the assumptions I said earlier, that higher order equations we are going to in a first order. That are the assumptions I am taking. So, yeah. And multilinear regression action. Whenever we will apply that multilinear regression analysis, these are the resultant equations. What? For skin friction and Nusselt number. So these are the graphs that for the magnetic parameter. So, but generally for the magnetic parameter, velocity profile will decline. But here we having the mixed nature. But due to the slip conditions, that mixed nature will come. Even for temperature profile, whenever we will apply the magnetic effect, that always temperature profile will raises. But here having the mixed nature, that due to the dual slip conditions. And here also in the chapter I applied heat source, but definitely that it must need to be increased temperature profile whenever we will apply the heat source. But here having the mixed nature, that due to the slip conditions only it was happening like that. Why means that whenever we will apply the like slip conditions at the boundary, generally velocity will be 0. But whenever we will apply the boundary conditions, it will become non-zero. That particle movements changes will be there in that movement. So that's why mixed nature will come. These are the multilinear regression graphs. And if you observe in case 1 having for the different non-dimensional parameters, in case 1 having the more dominance nature, why it was happening means that thermal conductivity nature in case 1 having more compared to case 2. You can go below. Here you can see here thermal conductivity nature in case 1 particles are having more compared to case 2 particles. So that's why their case 1 particles having the more heat transfer rate compared to case 2. Okay. Here, whatever I explained now in the form of a graphical, so that I wrote as a conclusion here. Next chapter. Yeah. So the difference between above chapter to this chapter is that I applied non-uniform shapes, like nanoparticle shapes with the spherical cylindrical platelet, and same magnetic effect and the heat source are applied. And this thing I already explained, 4.1, 4.2, that these are the transformations I already explained. Yeah. Yeah. This is the stop. So this is the modeling for like for the different nanoparticle shapes. Okay, that 4.19, 4.20, like 4.19 will represent for the viscosity, and 4.20 will represent for the thermal conductivity, and 4.21 for the density, and 4.22 for the specific heat. Yeah, these are the things. This is for the, like for non-uniform shapes, for spherical cylindrical plates. This is the modeling. Okay. Next. Let's go back. This is the numerical methodology. This is after applying the multilinear regression, these are the resultant equations for thin friction and Nusselt number. Yeah. In this chapter also, I applied the slip condition. That's why having the dual nature for the magnetic parameter. And here also that whenever we will apply that, like whenever volume fraction will raises, that flow momentum will raises, so that velocity profile will increase as well as the temperature profile also will increase, that you can observe. But little bit mixed nature here. Why means due to the slip conditions it was happening like that. Yeah, this one, in this having case 1 particles having the more than case 2, that it was also happening due to the thermal conductivity having high value than case 2. These are the thermophysical properties. These are the comparing results with the old published papers. Whatever I explained in the form of graphical, so I wrote here as a conclusion. In the chapter 5, that nanoparticles are with non-uniform shape, that case 1 having aluminum oxide and carbon nanotube graphene, and case 2 contains copper, silver, cobalt, and with base fluid as a water with the non-uniform shapes. And here one extra effect has been added, that suction effect has been added, and heat source and magnetic effect has been applied. Here you can see at the boundary. So by applying the suction effect, the drag force will reduce and keep like flow of momentum of the fluid will increase. That means velocity profile it will increase. This 5.1 and 5.2, 5.3 will represent the continuity, momentum, and energy equation. And here you can see that applying the suction effect in 5.4, you can see V equal to F naught. That one. Yeah, 5.4 and 5.5 will represent the boundary conditions. These are the 5.7, 5.8, 5.9. These are the like after transforming dimension to dimensionless transforming equation. And here that you can see that suction effect parameter in 5.10 V equal to F naught by mu square root of mu A. And these are the stream function. So after putting that stream function into a governing equation, you will get this resulting equation. And after applying the Lie group analysis, these are the similarity transformations. And after substituting this similarity transformations in that 5.1 to 5.13, we will get the governing equation further. That are the resultant governing equations 5.16, 5.17, and these are the boundary conditions. And if that FW will represent the suction, if it is greater than 0, it will represent the suction. If it is less than 0 means it will represent as a injection. This is the numerical procedure. Here A is there in the suffix, it will represent that initial boundary condition. B is there that away from the wall boundary conditions, it will represent the B. As I said earlier, so whenever we will apply the suction, it will reduce the drag force, then automatically momentum of the flow will increases. That means here velocity profile is increasing. Whenever the flow movement is rises, that automatically temperature profile also will rises. Here pi also. Whenever that volume fraction is rises, that flow movement will rises, and obviously temperature profile also will rises. Yes, heat source are syncated. Definitely, when I apply the heat source, and it will generate the heat, so that definitely that temperature profile need to rises, and you can observe here, and you can observe clearly here. When I apply the slip condition, their mixed nature is there. So here I remove the slip condition, so that there is no mixed nature here. This is the response surface technique. These are for different parameters. That these are the graphs. These are the streamline, and these are the, like tangential lines for the velocity. And what is the use of the streamline friends? You can analyze the flow path. And these are the thermophysical properties that are. So while doing response surface optimization, we need to choose these values like lower, medium, and high values. But for this, I given some coded names. X1, X2, X3 like this. Yeah, the same thing. Whatever I explained now in the form of graphical, I wrote here as a conclusion. Next, in this chapter, non-uniform shapes has been applied in case 1 that aluminum alloy, magnesium oxide, and zirconium oxide. And here case 2 and silver, aluminum oxide, titanium oxide. And that different non-uniform shape that the shapes are spherical cylindrical platelet. And further, porous effect has been included in this chapter, and linear thermal radiation has been applied. Viscous dissipation also applied. And here you can see that this is the porous effect, and that sigma B square is magnetic effect, and here mu HNF, that one will represent the viscous dissipation, and dou QRY, that one will represent the linear thermal radiation, and last term Q naught will represent the heat source or sink, and 6.4, 6.5 will represent the boundary conditions. So by using same similarity transformation, by putting the similar transformation in a governing equation, we will convert that dimension to dimensionless, and by putting the stream function, we will get below equation. This one we will get next further. They are the similar transformations, and these are the similarity transformations we will get from the Lie group analysis. That again we will substitute in that 6.1 to 6.13. Then you will get the below equation, and these are the final equations you will get. And these are the below will represent that dimensionless parameters having in this chapter. And this is the spectral method numerical procedure, and that cos will represent the Chebyshev function, And here -1 to 1, the domain will be the 0 to 1. If you substitute that -1 plus 1 in this dimension distance parameter, you will get again the domain 0 to 1. And this B11, that 4 factors you can find this element. And by partial derivating the governing equations, you can get the B11, B12, those things. And F and theta are the like unknowns we need to find. Velocity and temperature we need to find. After finding that Bx equal to R, we will write in the form of Bx equal to R. Finally, then we will get the result. These are the things I said earlier starting that we will choose the residues for the given governing equation. That is R1 for the momentum equation, R2 for the energy equation. That residues we will check. That 1 power 3 is there. That will represent that first equation, first variable, third derivative. And that 1 is there. First equation, first variable, second derivative. So next one. Like that only. Next, when it comes to the R2, that B22 power 2 is there. That will represent that second equation, second variable, second derivative. Next further. These are the that whenever using in spectral method, that boundary conditions will be transformed like this. And I applied in this like by using Python run these graphs, and these are the RSM. Whenever we will apply the RSM technique, and these are the graphs for the different and dimensionless parameters. And here that red and orange combination is there. It will represent the case 1, and that green and yellow combination, it will represent the case 2. And case 1 having more dominance if you observe. And this is the machine learning technique to gradient descent method has been applied, and their red dots will represent the predicted values, and the green dots will represent the truth values. And we can see that both are closer. So that means our truth data and machine learning gradient algorithm, whatever it was predicting data, both are almost same. For the heat source are sync, whenever we will apply that the heat will generate, the heat source are sync, so that due to that reason temperature profile will raises, and as well as for radiation also. And for Darcy parameter, velocity profile is declining. Why means porous medium will be there now, so it will, due to that, it will oppose some flow, and it will oppose the flow, and that's why that velocity profile has been decreasing. You can see here, and there for Eckert number, that temperature profile is raising. Why means that shear forces is going to be converted to any heat. So due to that reason, for the Eckert dimensionless parameter, temperature profile will raises. And these are the thermophysical properties for RSM, that are the coded values, and these are the comparison like a spectral method and the shooting method, both comparison I did. Yes, that whatever I explained in the graphical way, that I written as a conclusion here. In this compared to previous chapter, in this chapter I applied the difference is in the previous chapter I applied non-uniform shape, and in this chapter applied the uniform shape, and that extra effect as suction effect has been added, and the multi-line regression has been applied. And these are the, and you can observe here that in 7.4 S0 suction effect has been included. That I explained all the terms about previously. These are the transform, like a dimension to dimension transformer governing equation. These are. These are the final governing equations. So after doing the similarity transformation by substituting the suitable assumptions, and these are the final equations you will get, and these are the final boundary conditions. These are the suitable assumptions and have been considered. And this is the numerical procedure for the spectral method for this problem. I explained already the coefficients and how we do. And whenever I apply that multi-line regression for Nusselt number, and I got the above equations for the when I consider the radiation, Eckert number, and heat source sourcing and suction effect. And in this, if you observe in here, case 2 having the more dominance than case 1 for different dimensionless parameters. Here also you can observe that whenever I applied that machine learning technique, that the red dots will represent system predicted values, and the green dots will represent the truth values. That means what are the results we got from truth values means what are the results we got from the numerical technique, and the red dot that what are the results got from the machine learning technique, and both are almost same. Okay. And suction, so that it will reduce the drag force suction. That's why that velocity profile will increase. That when flow rate will increase, that obviously temperature profile also will increase. Yeah, I said earlier. And for the Eckert number, that it will shear forces, it will be transferred into a heat. So that's why for the Eckert number also that temperature profile will raises. This is the like results comparison with the spectral method and shooting method. These are the thermophysical properties. So that up to now, what are the problems I did that are by using stretching surface, and in chapter 8 and 9, the geometry is wedge, and in each chapter applied nonlinear thermal radiation and the buoyancy effect, and in both the chapters like nanoparticle shapes are uniform only, and here 3 cases are there, and base wood as a polyethylene glycol and water both combination, and case 1 single nanoparticle and aluminum alloy. Next, in case 2, aluminum alloy and zirconium oxide both hybrid. Next, case 3, aluminum alloy, zirconium oxide, magnesium both ternary. So here it will represent the angle, and V naught kinetic energy, B magnetic, and Q, that is, it will represent the nonlinear thermal radiation and gravity. So it will pull the downside, and buoyancy will have opposite. It will apply to opposite to gravity. And here U, that small v will represent the velocity, and capital V will represent the potential velocity in a space domain with respect to time. Here you can see that, and the T will represent that this is the unsteady, and here you can see that capital V is that it's a potential velocity in a space domain with respect to T, and here you can see sigma square magnetic effect and porous, and here it will represent the buoyancy, and in other words you can call it as a natural convection. And here in this applying heat sink, I am applying. Before chapters I applied heat source. That means that definitely temperature profile need to rise. Heat sink means that temperature profile need to decline. These are the boundary conditions. And after substituting the steam function in the given governing equations, you will get this 8.6 and 8.7. Yeah. So after substituting that similarity transformations, you will get from the Lie group analysis. After substituting the that suitable similarity transformations in the governing equation by taking the thermophysical properties, by taking suitable assumptions, after substituting all, we will get this equation, resultant equations. These are the dimensionless parameters. So this is the numerical pressure for this. Again, in chapter 8 and chapter 9, usual shooting method BB4C and BB5C. These are the boundary conditions. As I said earlier, initial boundary condition will be represented with A, and away from the wall boundary condition will be represented with B at the suffix. For the N will represent the thermal radiation, so that obviously that temperature profile will rise. For the natural convection, that for natural convection also it will push the up. So whenever it dominance will be more, means that it will push the particles, so that when the particles are moving freely, that temperature profile will raises. Delta 1 will represent that heat sink, as I said earlier. In this chapter, applying the heat sink, that so that temperature profile will decline. So you can see there. And in this multi-integration analysis has been applied. So the case 1 is going to be represented with red color, and case 2 with gray, and case 3 with the blue. And here, in case 3 having more dominant. That generally what will happen when you mix that more, like when it comes to the nano and hybrid, that hybrid nano particles, heat transfer rate will be more compared to single nanoparticle fluid. Again, there is no guarantee of 100%, but in most of the cases, it will be like that. And in this, in case 1 and case 2, case 3, you can see that whenever comparing the tooth values and filtered values that which we got from the machine learning technique. And the table 8.1 will represent the thermophysical properties, and these are comparison of results. Table 8.2 will represent. Yeah, whatever I explained now in the form of graph, that's written as a conclusion here. And chapter 9 In this, what is the difference between chapter 8 and chapter 9? Means in this extra and uniform shapes only considering, and this somewhat extra is considering like suction effects is considering and partial slip conditions is considering. In this case, whenever I consider that suction effect and partial slip, we observe that in chapter 8 that ternary hybrid nanoparticles having more heat transfer rate than case 1 and case 2, that means nano and hybrid. But whenever I applied suction effect and partial slip, in case 1 having more heat transfer rate, that means nanoparticle is having more heat transfer rate than hybrid and ternary. There you can see here, and why not this? B is there, why not that? There you can see that suction effect and TS1 that it will represent that thermal slip factor. And these are the like similarity transformations. After putting the steam function in the governing equation, we will get resultant equation. After taking the suitable assumptions for the thermophysical property, that the final governing equations and the boundary conditions are this. These are the contour plots. That what is the use of this contour plots means that you can analyze that at the particular region what is the heat transfer rate is happening. These are the contour plots for the different dimensionless parameters. So these are up to now I seen for the mission like truth values and tweeted values when I compare. Up to now I shown only in the form of graphs only. Here in the form of data I am showing here truth values and tweeted values. You can see that almost similar. This is the chapter 10 and the conclusion. In chapter 3 use the BUP forces solver methodology, and in this what I analyzed in case 1 having more heat transfer rate than case 2, and in chapter 4 methodology used at BUP forces solver, and case 2 having the more thin friction transfer rate than case 1. In the chapter 5 methodology used BUP forces solver, and next further in this also having case 1 having more heat transfer rate compared to case 2. And chapter 6 that methodology used is the spectral method, numerical method has been used, and so in this having case 1 having more heat transfer rate than case 2 nanoparticles, and in chapter 7 have used the numerical technique is the spectral method, and in this also having case 1 having more heat transfer rate than case 2, and in chapter 8 case 3 here case 3 that means ternary hybrid nanofluid having more heat transfer rate compared to hybrid and nano. And in chapter 9 when I applied suction and partial slip effect, case 1 having, that means nanoparticle having more heat transfer rate compared to case 2 and case 3. These are the sum of the references. That's it. I need to say that at the end to some other people, thank you. And first and foremost to my guides are Dr CSK Raju, and he known to me from my 10th standard. So like he's a God gift for me, actually, to be frank. That one word I can use. Thank you for his endless cooperation, and I need to say thank you to our HOD sir, Venkatesh Garu, and our principal sir, Atul Kumar sir, and Provis sir, VC sir, and RAC members, DRC members, and faculty members, everyone, and Nagarata madam also. And when I asked her madam after submission of thesis, she given immediate reply. Thank you, madam. And for all the people, scholars, everyone, and who supported and who encouraged me in the journey, thank you all, everyone.
Sir, can you go? Question.
Okay. Yes, sir.
Yes, sir.
Like now, the session is open for questions and discussion.
Examiners, if you have any questions and comments, you please go ahead.
Yes, sir. So before that, is there any questions from the audience?
Any questions from the audience?
What is your dominant case 1 to case 2? When you say dominant, so that means case 1 having more nature, sir. That means heat transfer rate. Yes, sir. It's like more. Yes, sir.
Okay, then in the absence of the questions from the audience, I will ask few questions.
Sir, there is one question from the audience. They are
Please.
going. I will let
Okay.
you know.
Yes, sir.
Okay, sir.
Okay. During the initial part of your presentation, in around 16 or 17 slide, you have mentioned that you have used a couple of packages from MATLAB, SQLM and that, right? No, that is not inbuilt, sir. And you have said that alpha means in the form of graphs and tables. From those graphs and tables, what you infer, especially that actually the results will come in the form of numerical data, sir. So whatever the data will be there, that will be, if you give the plot command, means the data only will be represented in the form of graphs. That is in future or yes, sir. These are whatever the after transformation from PD to OD, whatever I got the equations, the Goring equation. That equations will directly non-linear equations MATLAB can't solve. So that's why that will convert into a non-linear to linear. First, that methodology will be there before going to coding. Methodology will be there. We will convert that non-linear to linear. Then we will go for coding. Then MATLAB can solve. And yeah, there are some symbol solvers are there. You can use Mathematica that are direct solvers. That they are user friendly compared to MATLAB. So in all this, it's not a technique, sir. It's not a numerical technique. It's not an analytic technique. That the given what are the governing PD equations are there. There are some numerical techniques are there which can solve direct to PD also. But that I developed that, I and my guides are developed numerical techniques that are which can solve ODE only. This Lie group analysis will be helpful to convert the PD equations into an ODE. When the first time this Lie group analysis was, who did first time this? Who developed this technique first? These people, sir, Kandaswamy, R.K. Das, these people. So fundamentally, group analysis, who developed that? Actually, when I studied related to fluid dynamics, so I came to know that these people did. So R.K. and Das and Kandaswamy, these people, and I was motivated from them, and I proceeded in my study. Group analysis and will be leave only. Analytical type. It's group analysis, but very advanced analytical type. One of the supreme analytical. And what you are using is that basically you are using Lie group just to transform your PD to OD. Yes, sir. Right, and after that you are using some numerical display to solve that particular OD. Yes, sir. So you should know now because this is done by Sophie B. Yes, sir. Yes, sir. Done by Sophie B. Oh, sorry. She itself did this OD solve. So now onwards you must understand that. I mean, because there is one thing you can see. You are using this.
Maruti Prasad, sir, do you have any questions or comments to ask? Since you are saying you have a class to leave, like you can give your suggestions or comments, and then we may continue further with other questions and answers.
From my side, nothing is there, sir.
Yes.
Yes, sir.
Please carry on, sir. I have a class now.
Okay, sir.
Okay, thank you, sir. Thank you, sir, Maruti, sir. Thanks.
Sir, you
Thanks.
can go ahead with your comments and questions, please, sir.
Yes.
Sorry to.
Yes. No, sir. Sir, I am actually sorry to interrupt between the question and answer. Like one of the member, you have some class you want to leave. I thought, okay, first let him ask. You please continue, sir.
No, sir, it's over. You can.
Over.
You can get
Okay.
Sure.
Thank you, sir. Thank you. Yes, sir. So first of all, I would like to congratulate Dr. Dinesh Kumar. You have done a very good research. Even there are many established researchers. They have not published in a very short span of time. So how many years you have done your research? 3 or 5?
Sir, 3 years, sir.
See, it is really appreciable. Like you have presented 8 chapters and many chapters has been published in high impact vector journals in SCA and SCE, like 6 impact vector and tal. Having mathematics background and publishing in such a very good journals is not at all easy. So your guide is obviously a motivating force, but you are also worked very hard, so that we can very clearly observe from the publications. There is no hesitations in recommending the thesis. There are few small questions, and we expect you to speak more. So first, in equation 3.3, like you can see, I did not notice the slide number. Can you go to 3.3?
Yes, sir.
So here you are using for heat source or sink plus or minus sign. So obviously it is understood that for negative sign it will be heat sink and positive sign it will be source. And by
Yes,
chance,
sir.
if it is 0, it is absent. But later on, after dimensionalization, you are using only plus Q. Maybe like equation 3.9.
Yes, sir. In this study, using heat sink only, sir. No
Only
heat
heat
source only,
sink.
sir. That means plus only,
Okay.
sir.
You are
In
using
PP
only
I
heat
kept like
source.
this, but in thesis plus only, sir.
Okay. So in that case, you may remove that minus sign for better clarity. In the next chapter also, you have done the same. Like
yes,
in So in the plus or minus sign, if you are going only using for the heat source, you go only with plus sign.
Yes, sir.
Okay, now already I think you explained in the beginning also, and in the question also you have explained, but still I want to ask you, like
Yes, sir.
why
Actually,
you have chosen Lie group analysis for your analysis, and what are the limitations and advantages?
And when it comes to the advantages, like when it comes to the traditional transformations, it will be less time, and it is also will give accurate results, sir.
Okay. So compare with also which transform you are comparing? Usual transform means which you are saying?
That means we'll use no, sir, generally traditional transformations.
Which one?
Generally, like traditional transformations is there,
Traditional.
sir.
Yeah. Okay, like
there will
something
be
like
specific
Laplace
name, like
transform or Fourier transform or some transform you want to mention in particular, or?
yes, sir. Actually, I seen in some papers also just they mention like by using traditional transformations.
Okay. Because in general, like there are various transforms like Laplace, Fourier transforms, and others. Okay. So, what are the mathematical and physical losses will be there when you use similarity transformation?
Like that, we are like if you solve directly PDE to PD means that there will not be any loss, sir. That when you are converting PDE to OD, that there will be some loss of generality.
Exactly. So mathematically, what is the loss? Physically, what is the loss? And how you will justify that when initially we consider 2-dimensional problem, then we convert into 1-dimensional problem, and we get the results for 1-dimensional problem, but we say that are the characteristics of 2-dimensional problem. So there is a justification. Can you justify that?
That means, sir, what are the losses are there?
Yes.
That means
so
like
already you said like PDE is getting converted to ODE mathematically. Then physically 2-dimensional is getting reduced to 1-dimensional. Now the second question is, so now there is a mathematical loss, there is a physical loss. How we can justify the solutions obtained in ODE will be the solutions for PDE?
That's by using residual, sir.
No, the residual will not come here.
That means like
there is a physical explanation.
So when it comes to the numerical explanation, that if the residual value is like almost equal to 0 means that's the indication that exact solution and numerical like they are almost similar.
No, actually that exact numerical that you will see in ODE to ODE only. We don't compare PDE to ODE. Okay, I will tell you. It is good that you are getting connected to the questions very well. It is like in one dimension, your plate is infinite in length. In one other dimension, that length is very small. Like in x direction, it is infinite in length. In y direction, that length will be something very less. So the changes in
Yes.
y direction will be highly applicable compared to changes in x direction. X direction is infinite in length. So the changes with respect to x direction will be neglected. So that's why the physical laws will not impact much.
Okay, sir.
Next question. Why there is no increment in the velocity profiles near the boundaries, like say slide number 30, for example. Slide number 30.
Yes, sir.
Okay, or maybe like one or two, like next slide, 31.
Yes, sir.
So you can see here, in general, the trend for velocity profiles will be something like it will go up initially and then come down and go up, go after that, in general.
Yes, sir.
But it is justifiable. Like yours is correct. It is not wrong, but you justify. You see, for
Yes, sir.
example, in heat, okay, in heat transfer in general, from 1 to 0, it will go like this. It is more general. But in velocity, from the whatever, even if we take with moving velocity, it will go up little and then come down and then it will go to the free stream condition. But in your case, slightly directly it is coming down. Any explanation?
That means due to slip conditions, it was coming mixed nature, sir.
No, mixed nature is okay. That is not a problem. I'm asking, like, it is like starting from the point 1.5, it is keep on decreasing. There is no boundary effects that is increasing and then decreasing. Like in general velocity profile will go some small parabolic nature in the near to the boundary for all the velocity profiles in general.
Why it was coming from 1.5, sir?
From 1.5 to directly down. Why the slope is not increasing and then getting down?
Sir, like in the boundary.
No, your answer is right. I just want justification. There is no wrong. It is correct. Nature is correct. Value taken, everything correct. You need to
Yes,
justify how.
I think you're asking that it will come like in the above, it will come and again it will down.
Yes.
Okay, it will depends upon the geometry, sir, if I am correct. Means.
No, not geometry.
Yes, sir.
It depends on other effects. Like you don't have much effects to improve near the boundary. You have taken a slip velocity in a very high slip velocity. Suppose if you have taken 0, 0.3, 0.5, then it would have gone raised up and then decreased. But you have taken very high slip velocity to the wall. So obviously it is coming down. That's all. Okay.
Thank you,
Next, like why multilinear regression is applied only for skin friction and Nusselt number? Why not for velocity or temperature? It is right. What you have done is correct. Just we want justification.
Yeah, we can apply for that also, sir. There is no.
No. Then why you did not apply? Like you would have seen in no literature, no one apply for either velocity or temperature. They will apply for only mostly for Nusselt number.
I'm going to tell the same thing. Actually, if you see for numerical results, in nowhere we didn't find for velocity directly for temperature.
Yes, even comparison also. Comparison also, they mostly do only for skin friction, mostly for Nusselt number, not even skin friction. Sometimes they do skin friction also. Yes, and even this all multilinear regression, the like sensitivity analysis, everything they do only for skin friction, Nusselt number and zero number, mostly in particular for the Nusselt number. Can you justify why?
That is why you are applying for this only.
Why not for velocity or temperature or concentration?
At present, my answer is that previous literature also they did like numerical
data.
They are getting from skin friction and Nusselt number, as you say, for squeeze wood only.
Yes.
By following the previous researchers, I am also doing for skin friction and Nusselt number.
Okay. Because physically, these skin friction and Nusselt number are very important because it will see the transformation of how you are impacting, how your effect. All the effects are boundary effects. You are applying near the boundary. So how the solid and fluid interaction will be there, that is more important than only in the fluid. What are the way fluid, like velocity, temperature, we will see. The interaction within the system only we will see. But all the effects, we are applying boundary effects. So how this impact will be there between the solid and the boundary, that interaction is more important than others. That's why we always see when we make some effort, like near the solid wall and the boundary, because all the studies what you are doing is boundary layer studies. So Nusselt number, skin frequency, root number, mostly we will see. In that Nusselt number we will see. Okay, in slide number 52. In the flow geometry, you have taken for slip velocity that is minus f naught. But in equation, you are taking v equal to only f naught. So in any one place, it should be changed. Maybe better in here if you keep f naught, because you are saying f naught for negative values, it is injection, and f naught greater than value, that is suction. So in here, in place of minus, if you keep only f naught, that will be more appropriate. Because you can see in the equation, like you go to the equations, governing equations. See, previous. So here you okay, minus is there. Okay, I did not notice them. Is minus is there or not there? Somewhere it is there and somewhere it is not there. Yeah. Like in the next slide, it is there, I think. Here it is there. So there it was not there. So you maintain any uniformly.
Okay, okay, sir.
Yeah, either you go better with the f naught, because you are taking f naught negative, f naught positive both in FW. So you may avoid this negative sign here.
Okay.
And next one, in slide number 59. So is it it is only 0.08 or it is 0.008?
Where, sir?
In general, we go 0.02 like that, like 2%, 4%, like that, 5% like that. In general, we don't go up to 8% at all. So it is 0.008 or 0.08?
0.008, sir.
Okay, means it is like in 1000, it is not in percentile, then you are going more than that. You verify that values maybe. Like in general, we go. Yes.
Yes, sir. I think.
Because in here, in this case, it is less than 1%. Less than 1% itself, you are having very heavy effect. So you verify that. I feel in general 0.0 only will come. 0.00 if it is coming, then it is like very high effect. You just verify that value. Maybe your computation results everything correct. Only the determination 10 or 20 you verify. Because in this case, it is not even 1%. Within 1% itself, we have very huge response for that. And in slide number 61, like there is no wrong. What you have taken is perfectly right. But can you justify why you have taken the magnetic parameter and Prandtl number combination to get the variation of Nusselt number? Why not others? Like you have taken in x-axis.
These parameters will affect the Nusselt number. So that what are the parameters first whenever doing that response surface methodology and MLR technique, sir? That what are the parameters? That means if you are applying for Nusselt number and skin friction, what are the parameters will apply the Nusselt number? That's parameters we will choose, sir.
Yes, which are the parameters that have very high impact? Those parameters you are choosing.
Yes, sir. Okay,
but still, this magnetic field is a different feature, and Prandtl number is the other different feature. You are taking both of them. Impact of Prandtl number will be very high in Nusselt number. Impact of magnetic field depends, sometimes less, sometimes high. But it is okay. So when viscous dissipation effect is more significant, like in one study, one
upon shear force, sir.
Okay, correct. So like in slide number 70, it is like very trivial. You should not use capital COS, small COS you use. Like by chance anywhere, if you would have used like that, you change it.
Yes, sir. Yes, sir.
Yes.
This is I changed it in PPT only. It was there, sir.
Oh, no problem.
Yes, sir.
And again, what about the spectral methods, limitations and advantage?
The main advantage is that you will get very less, sir. Like if you see BVC 4C and all, it is there is some inbuilt error is there, but when compared to like in this spectral method, this main aim is that the error it will try to make it almost zero. That means you will get more accurate results.
Okay. Then in this heat source or sink, you are saying, but you are taking always only positive values. In one of the figures, you said heat source or sink, but it was only having positive values. So that you carefully verify.
Okay, sir.
So and in slide number 90, so you can see the magnitude is gone up to 20 for suction in heat transfer. This is a little like very, very high because only for this graph it is like this. So you may verify only for this particular graph. Nowhere else it has gone like this. Like
Yes, sir.
0 to 20 it has gone only for this particular parameter. Okay, that's all. So I'm very happy that you have answered many questions. You have good understanding. You have done very hard work. You have published in many reputed journals and continue your hard work. And now, very simple question. Like, what is your contribution to the literature to award doctor degree to you?
Not getting, sir.
Okay. What is your contribution to the literature to obtain the doctoral degree?
My country, that means my contribution to
Your
the research.
contribution. Yes, yes.
Yeah, that means that I did. These are the very new things. As if I am correct, means these are the streamlines and these are the contour plot. These are very new. That nowadays that it is the trending and even is the machine learning technique. These are nowadays emerging. If I am correct, means that very few people did these things and all.
Okay, so in addition to the usual fluid dynamics approach, you have used something like response surface methodology and that multilinear regression and some other machine learning related ideas. So that you are feeling as a contribution, but still you need to explain something more. You have done already. You have done. Okay. To the chairman, like, is there any other questions or queries to be asked to the candidate?
Yes, sir, you can go
Hello,
ahead.
sir. Hello, sir. Sir, is there any other questions or
No,
queries to be?
no,
Okay, sir.
not right now. No,
Okay,
nothing
sir.
right now.
Yes. So may I announce, sir?
Sir, the comments we can check once, sir. I think.
Yes. So can you please
Yes,
show
sir.
the comments by the
Show the
external
comment.
examiners? And yeah, there are some 15 comments by the Indian other examiner, Dr.
Examiner, yes.
Sandeep. And
Yes, sir.
from the foreign examiner, he has given like the thesis is very excellent. He has given
Yes,
like
sir.
very good comments. He has highly appreciated the thesis work carried out by the scholar under the supervision of the guide. The Indian examiner, Dr. Sandeep, as well as me, we have given
Yeah.
like few
Stop
queries.
share and then again share, sir. Stop
Yeah.
share and again share. Ah, yeah, okay. Ah, yeah.
sir.
Yeah, now share.
I have also verified the revised thesis. To the best of my knowledge, the student has explained all the queries under the guidance of
Yes.
the guide. So,
Thank you, sir. Thank you. Thank you, sir. Thank you very much for the session, sir.
Thank you, sir, very much. So these are the, I will go through the slides one by one if you want.
yes,
You can spend
yes.
do a presentation. Yeah, your slide show.
Someone who is disturbing some.
That's also.
Only one thing, in few chapters you have used thermal radiation. Only in that chapters, radiation effects should be considered in the Nusselt number. Just in the
Yes, sir.
typing you verify. You would have
Yes,
done
sir. As
in
per
the
your
paper
suggestion,
correctly.
modified, sir, in thesis.
Just in the typing you verify, because like sometimes when you do many work, the small kind of mistakes may be possible. You would
Yes,
have
sir.
done correctly. Just verify wherever this radiation effect is there in Nusselt number, that effect you have considered or not in typing.
Yes,
Yes.
sir.
Yes, done. Okay. So shall we conclude, Siva?
Sure, sir. Sure. Thank you,
Yes.
sir. Sir, can you?
Yeah.
Thank
Yes,
you. Thank you very much for all.
Shall we conclude, sir?
Yes,
Shall
sir.
Yes, sir.
Okay,
So this gives me immense pleasure to say a few words about the work done by the guide and the scholar. Like Mr. Dinesh Kumar has done a good work on the topic Lie group transformations and the conducting flows with suspended hybrid nanoparticles under the guidance of Dr. CSK Raju. So the Viva-Voce presentation is good, and the candidate has presented very well. He has tackled and replied to most of the queries raised during by the audience as well as the examiners. And we are very satisfactory. The answers are very satisfactory. So I'm happy to recommend the award of a PhD degree in mathematics to Mr. Dinesh Kumar by GITAM Deemed to be University, Visakhapatnam. And hereafter, Mr. Dinesh Kumar can be called as Dr. Dinesh Kumar. Congratulations to the student and the guide. Yeah, and carry out your research in more effective way. So this is something like a key. The doctorate degree to you is just a key to enter into the research world, contribute more to the literatures quantitatively, qualitatively, and do good research.
Okay, thank you, sir. Thank you for your valuable
Thank
time.
you very much.
Thank you. And I thank the GITAM University for giving me an opportunity to evaluate the PhD thesis of Mr. Dinesh. And thank you all. Bye.
Thank you, sir. Thank you, sir. Thank you very much, sir. Sir.
So shall we conclude the meeting? Okay.
Yes.
Yeah, shall we conclude? Yes, sir. Yes, sir.